All right, welcome back to this second hour. So I'm going to continue on the topic of the vector space model and ranked retrieval. So remember what we said just before the break. Let me just summarize everything. When we looked into Boolean retrieval, we had Boolean queries, and all we output was a set of documents, a subset of the original repository. There was no ranking, nothing. It was just a subset. Now we want to extend the system in order to make sure that the results are ranked. But in order to do that, we need to find a way to compute scores in order to rank the documents. We looked at parametric search, which is one way to do it using several fields in some querying interface. But then we looked into something even more awesome, which is that if we switch to bag of words semantics, and now we count the number of occurrences of the terms in each document, what's called term frequency, we can actually represent the documents as vectors of numbers. We fine-tuned a bit. Of course, we could use the term frequencies, but we slightly modified that by also adding the inverse document frequency, which is just to account for the rarity of a term. But basically what we have is that these documents are now points in a vector space. We have a way of telling if some documents are very, very similar to each other, or on the contrary, further apart from each other. And now we throw in the queries, because what is a query? It's also text. So a query also has terms. A query can also be expressed as a bag of words, right? So if you consider that a query is also a bag of words and can be represented as a vector, then in your very big vector space, more exactly the first quadrant, because we only have positive coordinates, we have documents and we have queries. So you have, if I have this query right there, what is going to be the top ranked document that I'm going to return for query 2? What's going to be returned by query 2? Anybody? The ranked list of the top documents. So I'm in front of it, D3, yes, D3 would be the top document, and I also see it in Zoom. What after D3? What would you put after D3? D4, I see on Zoom. D4 is there, yes, absolutely. I actually don't know if D5 or 4, let's see. Because actually I have this. Oh, well, I just have one, but if I try to put, you see, from the origin, oh, it's almost the same, you see? So actually D4 and D5 are very similar to each other, right? So let's call it a tie. Let's say D4 and D5 are actually second and third, but in any order. And then we'd have D2 and D1, right? So you see, it's the dot product with Q2 that is interesting to me, right? So I really just look for the angle. All right, so we have indeed D4 and so on. What about query 1? What are the top ranked documents if I query with query 1, Q1? On Zoom, maybe? Nobody on Zoom? Yes, go ahead. D2, yes. You see what I'm doing here. Q1, yes, absolutely. D2 is actually incredibly close to Q1. What's the next one that you would return? D1, yes, I see somebody saying D1, absolutely. D1 is not very far away either. So you're correct on Zoom as well, right? And the next one would then be 4 and 5, and then 3. All right. But you see what's incredible. What question did I ask you? I said, what are the top ranked documents as answers to this query? Did I show you the query? No, I didn't show you the query. I showed you a vector in a vector space. That's an abstraction of the query. And you were able to answer it. So this is really because we are at a higher level of abstraction that we no longer see the query just as the words that are on the screen, but we use the vector space now to abstract things in terms of the angle. All right, so you have a good intuition. All right. All right, so I even added these rows here to give you the intuition. All right, so now comes the difficulty. We have to calculate, so in real life, we have a query incoming, but maybe we have, let's say, 100 million documents. So we have 100 million points in there. We need to compute the dot products with them. But even worse than that, that vector space that we're looking at here, it's not just 2 in dimension, just like on my screen. Of course, on my screen, I had to do it in dimension 2 because otherwise that would have been tough, right? But it's a high dimension. It's the number of terms there. So it means that I have a dimension like 500,000 is the dimension of my vector space. That's absolutely gigantic. And the dot product is the sum of the products of the coordinates over all of these dimensions. It's a gigantic sum, and we have to compute a huge number of such sums. Can anybody give me a good reason why computing the dot product is actually not that bad? Any good reason? On Zoom, maybe? Any good reason why the dot product is not so terrible to compute as it seems? Yes? Can we maybe use, actually, I was thinking maybe we can try the microphone. Would you like to speak in the microphone? Just so that those on Zoom can actually also hear us. There you go. It's also fine if you don't want to, right? But I think it's good if they can hear. Also, that's awesome. You also have the same ideas. That's another idea. Okay, go ahead and say it. Then we'll go to those on Zooms as well. I think it's the same idea. There were 2 things that you were saying here. So please repeat what you've just said.
So the first one is that the algorithm for itself for the dot product is very easy. So it's you can do it in linear time. And yeah, the other point was already.
And the other point is on Zoom. Perfect. So let's go on Zoom now. So indeed, the first point is correct. Is that it's rather simple to do. And now on Zoom, the remark is that most of the documents contain only few tokens, and you're absolutely correct. This is exactly also something that considerably simplifies everything. That's actually great. So perfect, you have the right thinking. And I see the other remarks, parallelizable and linear, you're absolutely correct. That it's something that we can indeed parallelize, and the fact that it's linear is also a good thing. So yeah, these are all good reasons. All right. Okay, so how do we evaluate a query? So we have this dot product with these huge vectors that have like 500,000 coordinates in there. And as you've just said on Zoom, there's a lot of zeros. So there's zeros all over the place, right here. And there's actually going to be just a few terms in the query in particular. The queries are very short. So just because of the query, there's going to be very few terms in there, right? So the dimensionality actually is not that big. You don't have a sum of 500,000 numbers. You really just have a sum of, let's say, 10 numbers, and that's already a big query if you have 10 terms in the query. All right. So in order to compute the inner product, that's the dot product. Sorry, I tend to say inner product or scalar product, but I'm going to stick to dot product because this is the way you're used to it. So it's the cosine of the angle, like the dot product of the renormalized vectors gives us the cosine of that angle. And that's a measure of similarity that we can compute like this, right? It's the sum of the product of the coordinates, but we divide everything with the product of the norm. There's a double bar there, right? Okay, but what are these xi, yi? You quickly saw it on the slide, pretty sure. What are these values right there in practice? What is hidden in X and Y? Yes, the TF-IDF. I see in the Zoom chat. Yes, absolutely. This is what it is. So we have the product of the TF-IDF T and D, so that's the term right there in the sum of the documents that we are scoring, and multiplied by the TF-IDF of the term in the query. So the query doesn't change, right? Q is the static value, that's the query we're solving. And we are doing that for every value of D, right? Because we're scoring the documents. So we're computing the similarity between the documents and the query. All right. Now, if we want to do this, we probably want to reuse the structures that we've had so far, because we had the standard inverted index. And the standard inverted index is like this. There's a B plus tree of all the terms, and then they are linked to these posting lists right there. So this is probably the place to start with in order to compute this dot product. So we should probably store the TF-IDFs in there, all right? If we store the TF-IDFs in there, then we can basically just, as usual, navigate left to right the posting list and compute the sums of the TF-IDFs, right? But in fact, that wouldn't necessarily be very efficient, because in the TF-IDFs, the term frequency depends on the postings, right? What is the subscript of the TF? It's the term in the documents. So the term is the row, that's the term. And then the document would be each posting is a different document. So for the term frequency, it kind of makes sense. But what is the IDF of a term? Is there actually anything in there that could help me compute the IDF? Let me give you then something that might surprise you. These document frequencies have been in the standard inverted index almost since day one of this course. When I introduced the standard inverted index, the document frequencies were already in there. I just didn't call them that way. So where are my document frequencies? They're right here on the screen somewhere. On Zoom, maybe? Yes, so the purple boxes, right? This is what you mean. Yeah, exactly. These are the document frequencies. That's exactly what this is. These are the document frequencies of the terms. It's the number of documents that contain the term. So we are not far away from the IDF once we have that, right? So we can basically store the IDFs at that place, right? So another reason why we don't want to store the TF-IDFs in there, we compressed that part, right? We compressed the document IDs. So the part that is in here, we spent an entire week before the Easter break compressing that. How did we do it? Because we assumed these were integers. These were even increasing integers. But the TF-IDF, these are doubles. So now, how are we going to compress things if we don't have integers anymore, right? So that's also one more reason why we don't want doubles in there. So what we do is we only put the term frequencies in there. These are integers, and we outsource the inverted document frequencies to there. So very often what happens is that we don't necessarily compute the log, but we compute some kind of integer part of the total number of documents divided by the document frequency. So it's half of the computation of the IDF, if you want. Half of the computation, we put it in there instead or in addition to the document frequency, and then we compute the log. All right? Is everything clear? I sense that, I mean, it depends on the days, but I sense that there's not a lot of energy today. Maybe it's recovering from the Easter break. Right. There's also been lunch, right? So after lunch, it's of course always needs time. All right. So But that's for the documents. So the TF-IDFs for the documents, that's solved. We put the TF in there, the IDF in there. What about the query? Well, the TF-IDFs of the query, that's the easy part, because the TF-IDFs of the query is something that never changes. It's where it changes with the query, right? But it's the same for all documents that you want to rank. So that's something that you can just compute. There's not so many of them. That's the easy part. All right. So now we adapt the structure. So we have put the TFs in the postings, the IDFs in the purple boxes, and the TF-IDFs for the query somewhere else. So now here's what's going to happen. These little boxes that I put there, the green, these things here, these are called accumulators. There is one for every document, document 1, document 2, document 3, and so on. These are, you can consider them as like registers or places in memory where we store a number, right? So we have these the doubles, let's say. There's a double here, double here, double here, double here. These are called accumulators because we just accumulate the scores. We are going to traverse that structure in some way. And as we traverse it, we just update the buckets right there by accumulating and accumulating the scores of the documents, right? So now, if I repeat my formula here, my dot product that we're calculating, I have the TFTQ times IDFT times TFTD for the document times IDFT divided by the norms. Now, you notice that this one comes twice. The inverted document frequency is the same for the query and for the document, right? That's just only subscripted by T. So it's actually the square of that. And then we multiply TQ, that only depends on the term right there, because Q is a constant, and TF of TD comes from here, and IDF come from there. Now, the norm of Q is a huge constant that is just outside of things. You could even drop it. I mean, we'll see later that it's just a renormalization factor, so it doesn't influence the ranking anyway. And here, the norm of the documents, this is something we can store at some other place, right? We can just keep a map from the documents to their norm. So this is basically where things are coming from. And the idea of the accumulation is that every, I was about to say term, but I don't want to confuse you. You know that when it's a product, we say it's a product of factors. And when it's a sum, we say it's a sum of terms, right? Term is what you call what there is in a sum. The problem is that it's an information retrieval lecture, so term also means a word in the document. So this here is a term in the mathematical sense. It's a term in the mathematical sense because this is what we sum, right? We just sum over T for every D, right? So for every postings here, every postings, there will be one such mathematical term. And we are going to accumulate these mathematical terms in the bucket for document D for every T. All these terms for T go in there for document, in that case, document 4. And then we do it for every document. Now, here's the thing. There's two ways we can do that. The first way we can do that is called term at a time. It means that we start doing it with ETH. So we traverse the entire postings list for ETH. And then we go with Zurich. Again, we do all documents. And then we go with computer and so on. Of course, the terms in the query, right? Not those that are not in the query. So I'm assuming these are all the terms in the query. Term at a time means like this. Right, I go top down. The other way is document at a time. Document at a time means that I traverse this, starting here, left to right, but in parallel and concurrently. So this is why I now have my row like that. That's called document at a time. It's the same. It gives you exactly the same results. It's just the two ways that you can organize your computations. At the end, you will have in your accumulators everything that you need with exactly the same results. So I have an animation for you to make it absolutely clear what's going on in there with the example of ETH Zurich computer. Maybe that's somebody who wants to study computer science at ETH. And we are going to do it first term at a time, and then we're going to do it document at a time. Okay, so term at a time. So we start here with ETH, and we go from left to right in the posting list. So we have ETH document 1. So that gives me a TF-IDF, right? So the TF of ETH in document 1 is right there. The IDF is in here. And then I have the same for the query out there. So I just compute, you know, this big awful thing right there. There is one for each postings. So I compute for this posting right there, and I plus it into the accumulator. It was 0, and now it just, I use these bars here to actually visualize the numbers, right? But it's actually just a double or a float or whatever you want it to be. And now I increase my float or my double for document 1. Then I go to document 2. So you see it was at 0 because when you start at 0, and then I increased a little bit by this TF-IDF product. Then document 3, document 5, document 6. And you see document 4, nothing happened, but it's because it's not in there. Okay, I'm done with ETH, now Zurich. Document 3 gives me this TF-IDF awful thing that I sum up in document 3. So you see there's a small increase in there that's accumulating. The same in document 4, it was 0, now it's no longer 0. I'm done with Zurich. Now computer, document 1, you see the small increase. I accumulated document 1, and document 2 is going to increase. There you go. Document 4, there you go. Document 5, there you go. So this is the evidence accumulation. And you see that I just walked left to right and then top down. That's called term at a time. And at the end, what am I going to return for the results for that query? Can you give me the order in which the documents are going to be returned? Maybe in Zoom then. We have answers in Zoom. What will I see on my query results page? 5, yes. Do we agree on Zoom? Yes, so 5 then. You can actually see it on the screen. Somebody gave the answer right there. So we have 5, 6, 1, 2, 3, 4. So let me see. Let's control that. Okay, the highest one, so that's 5. I could actually take my stick right there. So you just need to go like this, right? So 5, then 6, then 1, 2, 4, 3. So that's the second answer. The disagreement between the two answers was between 3 and 4, right? So you said 5, 6, 1, 2, 3, 4, and then the second answer is 5, 6, 1, 2, 4, 3. So you really have to zoom in, right? Here, 4 is slightly above 3. Right? So this would be the last answer, right? 5, 6, 1, 2, 4, 3. Okay, who is following? Okay, and on Zoom, who is following? Okay, I see raised hands as well. Perfect. I see hands like this in Zoom. All right. Okay, just making sure that everybody is with me. All right. So let's do the same thing, but document at a time. So document at a time just means we concurrently visit the list, starting here, and we just go left to right. So it means we start with document 1 and we accumulate, all of the document 1s. And in fact, now we are done with document 1. We already know the score because nothing else will come anymore because document 1 is done. Now document 2 here, and we are done with document 2. Document 3, there's also document 3 here. Then document 4 and document 4. Document 5 here, and then document 6. You see, what you have here is exactly the same. If I go back to the slide before, I had exactly the same thing. The only thing that changed is the order in which I did it, but that's pretty much it. All right. So what's the complexity of what we just did? So we built these accumulated scores. And now what's the complexity of what we had to do to get the order of the output? If we have n documents, what is the complexity of outputting them. Yes? N log n for sorting. So that's a very good suggestion. Does anybody have another idea than n log n? Let's do a thought experiment. Give me one place where we see ranked results that you use every day. Yes, Google or DuckDuckGo or Yahoo or Bing or all of them, right? So search engines. How many documents are there? A lot, right? Billions, trillions. I don't even know how to count. So trillions of documents. How much time does it take for the results to appear in Google or any search engines? Let's say, okay, so 100 milliseconds. Those 100 milliseconds feels like n log n with a trillion documents. Just want to make you think. Your answer is correct, basically. It's obviously, we've learned that in algorithms and data structures. If you sort something, the optimal way of doing it is n log n, right? That's a known fact. So how come then that if I put a query on Google, it doesn't take n log n in order to return the results? Caching, maybe, yes. Any other ideas? Caching, it would mean that it's cached, but what if I type a word that's never used or used in like 100 websites? It's going to be just as fast, right? So how can it be? Pre-computed, I have the same idea on Zoom. Hash tables. Let me guide you. There is an explanation that is, it is related indeed to data structures, but it's more related to what we do not do than to what we do. Let me put it that way. I have something that gives you the results in log n, that will display the results page in log n. That's surprising, right? Log n, but how come that? Normally when we sort, it's n log n. Okay, let me give you the solution. You're almost going to be disappointed when I tell you the solution, really. So what we do is that indeed, we need to sort in n log n. But the thing is, instead of sorting, what we are going to build is a priority queue and not directly the sorting. So a priority queue takes linear time to build, right? I think I said log n, I should have said n, so linear time. So a priority queue takes linear time to build, right? But it's not n log n because I haven't sorted yet. I just built a structure that I can then use in order to sort. So once you have built the priority queue and you want to get the sorted list, you just extract from the priority queue all of the results, right? And this is where the log n comes from, because then you have to n times take log n in order to retrieve the results. That's the n log n that you get in the sorting algorithms if you use a priority queue. But what is there on your page, result page? There's not the whole internet, there's only the top 10 results. And that's the key. We only want the top 10 results to display to the user. So it means that I go ahead and kind of sort with a priority queue, except that I'm only retrieving the first 10 results. So I do have this log n, but only 10 times, not n times, 10 times. Right? That's the solution to the riddle. So that's one of the important things to remember today. So we can, in linear time and not n log n, retrieve the results. So we don't have this extra factor. All right. So log n is to extract, right, from the priority queue, not to build it. All right. And we'll see, because then you're going to tell me, okay, yes, but if there's a trillion documents and we are not n log n, but we're still linear, then how come it's 100 milliseconds, right? This will be something we'll see, I don't know if you have time today, probably next week, because we can have inexact retrieval where you actually don't do it on the entire data set, but you eliminate some of the obvious documents. All right. Okay, so now this lecture, so the part on vector space model, finishes with a restaurant menu of the options you can have to build your vectors. So I told you TF-IDF is kind of the de facto choice that a lot of people use and the first thing that would come to mind. But actually, there's other ways to do that. And people came up with a codification of the ways that you can actually populate your vectors. And I'm just going to present them to you, a few of them. They basically are encoded with letters, and then you have a combination of letters that tells you the way you put your weights in the vectors. So for the first, let's start with the term part, the term frequency part. The natural one is to just have the term frequency for the term and document. So it's basically just the identity function, right? That's the one we used for the TF part of TF-IDF. But there are people who do it differently. And instead of just directly using the term frequency, they use this 1 plus the log of the term frequency. And they just put 0 if the log cannot be computed. So that's just the singularity right there. So basically, instead of having this linear term frequency, they use a logarithmic scale, right? So this is another way that you could compute your weight. So instead of the term frequency, you use 1 plus log of the term frequency. So that basically means that if you start having a lot of terms, then one more term does not have the same impact as one more term if you don't have a lot of them. That's what the log does. All right. This is another one that's called the augmented term frequency scaling that is kind of doing this. It's a skew of the curve that basically says, even if you don't have a lot of occurrences or none at all, you still have a non-zero weight here, and then you skew it. So it's a tilt that you do here of the curve, right? And this is just the mathematical way of expressing it, but we just basically skew the curve like that. So we have, this is N, then it was L for this, and then we have A for this one. There's also the Boolean way. So the Boolean way is, okay, we don't care about the term frequency. We just put a 0 if it's not in there and a 1 if it's in there. Well, that's what we've been doing since the beginning of the semester, actually, right? But basically, that just comes down to a vector of Booleans then, if you only have the term frequency part, right? So either it's not there, or it's in there and you put a 1. So that's basically just the set of words. Basically, you fall back to the set of words. Okay. And there is here yet another one that is that actually looks a lot more complicated, but it's just, let's say it's the imagination of the mathematicians who derive ways to compute the weight. Actually, it's not random. The reason they came up with that is that there's a whole reasoning behind, like probabilistic or based on language models, as we will see at the end of the semester. All right. All right, so these are 1, 2, 3, 4, 5. So N, L, A, B, and L. Okay, so there are 5 possibilities for the term frequency. Then we can do the same thing. We have a menu for the document frequency. What do we do with the IDF part? So the first idea is nothing. We just do the TF or whatever flavor of TF we have, and we don't put any DF or IDF. Nothing. So we just use 1 all over the place. Or we use the inverted document frequency. This is the one you already know, right? The logarithm of the maximum number of documents divided by the document frequency. That's the good old inverted document frequency. It's the IDF that we've seen, right? So N if there is none, T if we use the IDF. So this is the IDF, right? Depending on the document frequency. Then there is what is called the probabilistic inverted document frequency scaling. All right. This one has this maximum of 0 and the log of blah, 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 blah. This is pretty much what it does, right? It basically also goes down, but it doesn't go down all the way to infinity. It goes down and then it reaches 0 when you have half of the documents. So the motivation here, we will see, I think, in 2 weeks, it's if you apply Bayesian reasoning and probabilistic reasoning, then that gives you weights that look like that. Right? But I'm going to come back on that. But anyway, this is P. Okay, so we have P, T, and N for the inverted document frequency. So until now, we have 15 possibilities, right? 5 for the term frequency, 3 for the document frequency. So that's already 15 combinations, to which I need to add the normalization. What do we do with the normalization? First, nothing. We don't renormalize at all. N. It means that we keep the vector like it is without dividing by the norm. Second, the cosine normalization. This one we've seen. This is the one I've showed you in the last hour, right? So this is when we divided by the Euclidean norm and we brought it back to the unit sphere. So we use the C in order to denote that one. And there are other ways. There are ways that you can, instead of renormalizing with the cosine, you can also renormalize by the byte size, so the actual size of the document on disk, right? And maybe you can put an exponent in there, but that's basically just the file size. And then there is also a pivoted normalization that does the same kind of things that when I told you about the skew of the term frequency, it's again a pivoting of the curve like that to pivot the normalization. All right. So what I showed you is just a restaurant menu, right? I told them, okay, these are the starters and these are the main dishes, the entrees, as they say in California. And then you have the desserts and so on and so on. So it's really just going to the restaurant and asking for your menu. And the way it works now is that people are going to give you codes like this, that look like this. It's called the smart notation. And it works like this. Here, this is how you build the document vector with the document weights. The first one is giving you the term frequency mode out of the 5 that I showed to you. Actually, there's a few more, but I showed you 5. So A, for example, it was the A. Let me scroll back. This A right there. A. Let me come back. A is augmented term frequency. T means we use the inverted document frequency, the IDF. And C means we use the cosine normalization. So if I tell you ATC, then you know how to build the document vector of numbers. What you have on the right is the query. For the query vector, here we use the sublinear term frequency to modify the term frequency part. We don't use any IDF, so it's the natural document frequency, that's the N. Let me scroll down, scroll back. Where were we? Here, the N right there. So that's the end. That's for no inverted document frequency, but it's also called natural document frequency, right? So you don't scale with an IDF there. And here B means that we renormalize the query with the byte size of the query, right? It's the number of characters in the query, all right? So these are 6 letters, 3 for the document, 3 for the query, and that tells you exactly how you compute your vectors. Now there's a few considerations, is that for the query, it's very common that we use here for the document, the inverted document frequency, but we don't use any for the query. The reason is that it's already on one side. If we add it here as well, we just square it, but it's a bit redundant, right? So this is the reason why often on the query side, we put an N and we don't add the IDF all over again, right? Okay, so now I'm gonna also give you that. Let's try to build the code that we've been using with our TF-IDF vectors. What was the code? So let me scroll back. So we had the TF. So the TF is N, right? When you just cite the TF, so it starts with an N, both for the document and the query. Then we had for the document frequency, we use the inverted document frequency. So we have a T, so it's NT. And the normalization we used was the cosine normalization. So that's NTC. So when I said over the entire lecture, we use TF-IDFs everywhere, we use the NTC menu. of the restaurant's menu. That's basically what we do. So it's basically NTC that we use today. But now you know that it's actually flexible and you can change the weights that you use in your documents, because you saw that what we've been doing with the dot products and so on, it's completely orthogonal to the weights. It doesn't care about what the weights are. So this is why you can decouple the two and pick your weights and separately compute the dot products. All right. That's actually my last slide for that lecture. And since I see that you're missing a bit of energy, I'm going to end for today right here. I'm just going to ask if you followed what I've been telling you, and then I'll just release you. All right. Let me just prepare the question, make sure that I'm logged in. Okay. There you go. So here I'm just making sure that you followed. If there's anything you didn't understand or I was too fast on some things, then ask it on Mattermost, let us know, send us an email, and we'll happily answer. Or you can also ask questions next week, of course. So I'd be happy to answer. All right, let's see. Okay, so we have a majority above 80%. That's perfect. So the rhythm was fine. Okay. And to which I should add that, of course, there's a book, right? There's the information retrieval book that explains it as well. And so if you didn't understand what I told you, then you can just read the book and you will find another explanation for the same thing. Right. Okay, that's perfect. That's exactly as it should be. All right, so that's actually it. So thank you very much for coming. Enjoy the exercise session, and so I'll see you next week again at 2, and we'll just continue with a few optimizations. And then what's next in the semester is the evaluation of querying systems, the probabilistic information retrieval with a bit of math, and the language model part, which is actually quite fun, actually. The language model part, there's going to be cool practical exercises. All right, so thank you very much, and see you next week. And thank you, Abhishek, for the moderation. Goodbye.